Have you ever wondered why everything in the universe is spinning, and yet we feel completely still? The Earth turns at over 1,000 miles per hour, orbiting the Sun at 93 million miles away, while the entire solar system itself races through the galaxy at nearly 500,000 miles per hour, and still we don't feel a thing. Our heartbeat doesn't tremble, our breath doesn't sway, our coffee sits undisturbed in its cup, as if we were frozen inside a universe in motion. But what if that stillness is the greatest illusion of all? What if the quiet you feel right now, the warmth of wherever you are, the slow settling of your breath is not the absence of motion, but its most perfect expression? What if time itself is just the echo of a deeper rotation, one that began before atoms, before light, before memory, before anything had a name for itself? Tonight we drift into that mystery, not to find answers that close the door, but to open questions that fill the room with light. We ask not just why things move, but why nothing can stop moving, why every particle, every planet, every thought is a continuation of something that began at the very first moment of everything. So close your eyes if you'd like, let your shoulders fall, let the sound of the cosmos hum gently beneath your skin, and follow me into the spinning heart of everything before we begin. If this quiet journey finds you in a peaceful place, a gentle like or a soft tap on subscribe would mean more than you know. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now let's begin with the first question. Part 1. If everything in the universe is spinning, why do we feel frozen in time? Right now, even as you read this, even as your eyes move quietly across these words, you are traveling at speeds so enormous that the human mind was never built to hold them. The Earth beneath you is spinning at roughly 1,037 miles per hour at the equator, turning steadily and silently as it has for 4.5 billion years. It doesn't announce itself. It doesn't shake the walls. It simply turns the way the deepest things always do, quietly, without ceremony, at the same time. This spinning planet is racing around the Sun at nearly 67,000 miles per hour, a journey of 580 million miles, completed every single year so reliably, so silently, that most humans live entire lifetimes without once feeling its passage. And while all of that is happening, the entire solar system, the Sun and its family of planets and moons and asteroids, is sailing around the center of the Milky Way at nearly 490,000 miles per hour. A single orbit of our galaxy takes approximately 230 million years. The last time the solar system was in this exact position, dinosaurs were just beginning to walk the Earth. Yet the coffee in your cup doesn't ripple, the air doesn't drag, the stars appear still, and your heartbeat holds its quiet, steady rhythm undisturbed by any of it. How is this possible? The answer begins with a word that sounds simple, but contains one of the deepest truths in all of physics: inertia. Isaac Newton first gave it precise language in the 17th century. Though people had felt its truth long before an object in motion stays in motion unless something from outside pushes against it, an object at rest stays at rest for the same reason. Motion doesn't need a reason to continue. It only needs a reason to stop. This is the secret behind our stillness. We are not sitting inside a moving world, we are moving with it. Your body, the air around you, the ocean, the mountains, the birds asleep in their trees, all of it turns together, locked in a single, silent rhythm that began before any of us arrived to feel motion. You need contrast, a push, a pull, a sudden change in speed or direction. But there is no such change here. The Earth's spin is constant, smooth, and ancient. It is the same now as it was when early humans first looked up at the stars and felt wonder, the same quiet turning, the same invisible rhythm carrying them. Without their knowing, astronauts experience this on a grander scale in orbit. They travel at 17,500 miles per hour, circling the planet once every 90 minutes, watching 16 sunrises in a single day. Yet inside the spacecraft, everything feels calm. A floating pencil drifts peacefully. A water droplet hangs in the air like a small jewel. Nothing announces the extraordinary speed, because without resistance, without air, without friction to remind them, motion simply feels like stillness. This is what scientists call uniform motion, the principle that gives every smooth journey its quiet feeling. It is the same reason you can sip tea on an airplane, traveling 500 miles per hour and not spill a drop. You and the plane are moving together equally, so neither of you feels the other's movement. Only when turbulence arrives, that sudden unexpected change, does the body know it was moving at all. Earth's motion is seamless in exactly this way. No vibration, no friction, no lurching starts or stuttering stops. And because space is almost a perfect vacuum, there is nothing pressing against us, nothing to remind us that we are passengers on a world crossing the galaxy at impossible speed. Neil deGrasse Tyson once said, "We are on a space rock, orbiting a star that is orbiting a galaxy that is moving through the universe, and we call it home." It is easy to forget because our senses were never built for such scales. Our inner ears, those delicate, spiraling chambers that detect balance and motion, evolved to handle the scales we actually need. Walking, running, climbing, falling. Not the rotation of a planet thousands of miles wide, not the orbit of a star that takes a year to complete. They respond to acceleration to change, not to the steady glide of something that has always been this way. That's why you feel the lurch when a car pulls away from a stoplight, but not the smooth hum of the highway at 60 miles per hour on Earth. Everything moves with you. There is no start, only an eternal glide, ancient and warm, and completely invisible. And yet scientists can reveal this hidden motion with tools of beautiful simplicity. The Foucault pendulum, first demonstrated in Paris in 1851 by physicist Léon Foucault, is perhaps the most elegant proof of Earth's rotation ever devised. It swings freely back and forth, while the ground beneath it slowly turns over the course of hours. The plane of its swing appears to rotate, not because the pendulum is being pushed, but because the Earth beneath it doesn't need the stars to prove Earth's rotation. The slow, quiet drift of its path is the Earth's invisible turning, made visible one gentle swing at a time. If you've ever stood beside one of these pendulums in a museum, watching the slow arc drift slightly farther, each pass you've witnessed something remarkable. Time and motion merging right there in the silence of a quiet hall on a cosmic scale. This rotation is far from trivial. The Earth's spin defines day and night, creating the rhythm that all land life has organized around it, stabilizes the planet's magnetic field, which deflects the solar wind, that stream of charged particles the sun constantly exhales, and which would otherwise strip our atmosphere away the way it stripped Mars. Billions of years ago, without Earth's spin, our world would be scorched on one side, frozen on the other, and everything in between would be subject to radiation. No atmosphere could survive against. NASA's Goddard Space Flight Center notes that the planet's rotation has been slowing gradually over billions of years, mostly due to the moon's tidal pull, adding about 1.7 milliseconds to the length of each day every century. So even in our stillness there is change. Slow, invisible, but real time itself is gently lengthening, one barely perceptible heartbeat at a time. When we look deeper, rotation isn't just an earthly phenomenon, it is a cosmic signature. The fingerprint of how matter forms stars are born from collapsing clouds of gas and dust when gravity pulls that cloud inward. Whatever tiny rotation existed in the original cloud accelerates the way a spinning skater accelerates when she draws her arms close to her body. This is the conservation of angular momentum, one of the most fundamental laws in physics, and it means that spin, once begun, does not simply fade. It concentrates, it deepens, it passes itself forward. Every planet inherits this momentum. Earth's 24-hour rotation is a fossilized trace of that ancient whirlpool of creation, the original slow turning of a cloud of gas and dust 4.5 billion years ago, concentrated by gravity into the world we stand on. Now even the sun spins once every 27 days at its equator, dragging its magnetic field through space like glowing threads, and the Milky Way, our galactic home, turns once every 230 million years, carrying hundreds of billions of stars in a spiral dance that began long before our planet existed. The James Webb Space Telescope has captured galaxies so far away that their light has been traveling for over 13 billion years, and even those primordial galaxies so ancient they formed when the universe was barely an infant show signs of rotation. ESA scientists studying these early formations found subtle differences in the light coming from opposite sides, one side slightly red-shifted, the other slightly blue-shifted, the unmistakable signature of spin. The tendency to rotate is written into the universe's earliest memory. But how can everything be spinning and yet feel so still? Part of the answer lies in relativity. Einstein showed us that there is no absolute motion. Only motion relative to something else. From our perspective on Earth, we are at rest, and it is the universe that moves around us. From another frame of reference, the opposite is equally true. This symmetry is what keeps physics consistent, and what makes our stillness an illusion of perspective, beautiful and exact in deep space. Astronauts aboard the International Space Station orbit Earth at nearly 5 miles per second. But they experience weightlessness, not motion. Their sense of down changes every 90 minutes, yet their minds adapt. They float peacefully surrounded by stars that appear still, even as they cross an ocean every 10 minutes. We too are passengers in motion. Adapted to calm our stillness is a form of survival, a balance between what our senses can bear and what the cosmos demands of us. If we could somehow feel the motion of the Earth, the pull of the sun, the drift of the galaxy, our perception of time itself would unravel, because motion and time are intertwined as rotation defines days and years. It also defines the heartbeat of the cosmos. Time, as Carl Sagan once reflected, is woven into the very fabric of the universe, and we are the thread. The quiet you feel right now is not the absence of motion. It's the harmony of everything moving together. So when you close your eyes tonight, beneath the invisible turning of the stars, remember this: you are not standing still, you are gliding through a cosmic river, gently, constantly, endlessly. Each moment of stillness is just the universe moving too smoothly for you to notice. Take a slow breath. You are spinning, always have been, and the silence you hear is the sound of everything moving together as we drift deeper into the story. Let's look backward to the moment before motion began, when the universe itself took its very first turn. Part 2: Who set the universe spinning? If you could turn back time, not centuries, not millennia, but all the way to the first second after the Big Bang, what would you see? Not darkness, because darkness is the absence of light, and light had not yet learned to exist. Not silence, because silence is the absence of sound, and sound requires matter to carry it. What you might find in those first impossible fractions of a second is something that has no name in any human language, an event that was not yet an explosion, not yet a birth, but a first motion, a twist, a swirl. The universe taking its very first turn. The question of what gave the universe its original spin is not a question of philosophy. It is a question buried deep inside the equations of cosmology, inside the earliest moments of time, when matter, energy, and space itself began to unfold. Astronomers call that earliest window the Planck era, a period so early, so close to the very beginning, that our current laws of physics cannot fully describe it. We are approaching the edge of what human knowledge can reach, and standing there we can only infer and wonder. But what little we can infer suggests something extraordinary. The universe may have been born not in silence but in motion, not in stillness but in a gentle rotation today. Scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, detected by satellites like WMAP and Planck, have found tiny irregularities, small ripples in temperature only a few millionths of a degree apart, invisible to every sense we have, but visible to the instruments we've built with extraordinary patience and care. These patterns, these faint whispers, written in ancient light, tell us that the early universe wasn't perfectly uniform. There were slight differences, tiny variations in density and energy, and those differences, those barely there imperfections, grew over hundreds of millions of years into everything we see today: galaxies, stars, planets, life itself. But some researchers noticed something stranger woven into those faint temperature maps, a kind of large-scale alignment, a subtle twist in the distribution of those ripples that shouldn't be there. If the universe had begun in perfect randomness, they called it the axis of evil, mysterious pattern suggesting that the universe on the very largest scales might have a preferred direction, a faint cosmic handedness built into the fabric from the beginning. According to NASA's WMAP mission data and follow-up observations by ESA's Planck satellite, this alignment could mean one of two things. Either it is a subtle artifact of measurement, a trick of statistics, or it is evidence, quiet but real, that the entire universe once spun, if true. That original spin may have shaped everything from the spiral arms of distant galaxies to the very arrow of time. The reason the future feels different from the past, the reason we remember yesterday but not tomorrow. How could such a rotation have begun? The key might lie in something almost impossibly small: quantum fluctuations, tiny random changes in energy that occurred when the universe was smaller than an atom, smaller than the nucleus of an atom, smaller than anything we have language for, even in complete emptiness. These fluctuations happen naturally, as NASA's Goddard Space Flight Center describes. Quantum fields are never perfectly still. They jitter constantly, invisibly, unable to hold their own silence when the Big Bang happened. Those jitters were stretched and amplified by cosmic inflation, a brief but extraordinary expansion that made the universe grow faster than the speed of light in the tiniest fraction of the first second. That rapid stretching, like pulling taffy across the whole of space, could have turned some of those quantum jitters into swirling motions. The first cosmic spins, tiny by any measure, but universal, written into the structure of everything inflation theory proposed by physicist Alan Guth in 1981, explains why the universe appears so smooth, yet still contains the seeds of structure. But in recent years, data from the Planck satellite and BICEP-2 experiments suggested that during inflation, subtle rotational modes, known as B modes, may have existed in the primordial gravitational waves. These tiny curls in space-time, these barely there signatures, could be the fossil record of the universe's first rotation. They suggest that the Big Bang was not just an explosion, but a twisting birth, one that imprinted spin across every scale of matter, from the largest galaxies to the smallest particles to the electrons orbiting inside you right now. And this makes sense when we look at what happened next. As the universe expanded and cooled, matter began to form first quarks and gluons, then protons and neutrons, then atoms. Each carried tiny amounts of angular momentum. A whisper of the original spin passed forward like a secret through every stage of creation. When gravity later gathered them into clouds and galaxies, that ancient angular momentum was conserved. Concentrated, made visible, it became the arms of the Milky Way, the orbit of our moon, the turning of the Earth beneath your feet in physics. Nothing spins from nothing, motion must come from motion. And so the first spin, however small, had to exist from the very beginning, or nothing we see would be turning. Today, astronomers can see the fingerprints of that original rotation in the distant galaxies that still surround us in 2011. Researchers from the Harvard-Smithsonian Center for Astrophysics analyzed over 15,000 spiral galaxies and found a subtle preference in their rotation direction, a slight imbalance, a cosmic handedness that might trace back to the early universe's first spin, while not yet conclusive. This hint of a preferred direction in the cosmos suggests our universe may not be entirely random after all. There may be a hidden rhythm, a silent turn that everything still follows. Even dark matter, that invisible scaffolding that makes up most of the mass of the universe, yet has never been directly touched or seen, could carry a spin signature. Computer simulations by NASA's Jet Propulsion Laboratory show that dark matter halos, the vast invisible spheres surrounding galaxies, twist and rotate over billions of years, guiding the visible galaxies within them, like whirlpools guiding leaves without that rotation. Galaxies would tear themselves apart, the stars would scatter, the arms would unwind. It's as if the early universe set everything spinning, and even now, the echoes of that motion keep the stars in balance and the galaxies in their ancient dance. Still, the origin question remains: who or what began the spin? Physicists lean on one quiet answer: symmetry breaking in the earliest fractions of a second. The four forces we now know, gravity, electromagnetism, and the strong and weak nuclear forces, were once unified. A single seamless force, balanced and whole. But as the universe cooled, they began to separate. And when that symmetry broke, tiny asymmetries appeared tiny. Imperfections. Beautiful flaws in the fabric. Those imperfections, according to the European Space Agency, are what allowed structure, motion, and spin to exist in a perfectly balanced universe. Nothing could move, but a slightly unbalanced one could dance. We can see this principle mirrored everywhere in the direction galaxies spin, in the way atoms rotate, even in the way neutrinos, those ghostly particles that pass through everything, have a left-handed preference. They all spin in the same direction, as if the universe whispered something to them at the very beginning, and they have been faithfully following it ever since nature. It seems is not perfectly symmetrical, and that tiny flaw, that one small imperfection in the original balance, is what allows everything to turn. Some scientists have tried to detect whether the entire universe is rotating in 2020. Astrophysicist Lior Shamir from Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. He found that galaxies in one half of the sky tend to rotate more in one direction than the other. A subtle but consistent asymmetry, suggesting a large-scale cosmic spin. This doesn't mean the cosmos is spinning like a top. Rather, it might mean that the fabric of space-time itself once twisted slightly during its expansion. Even a subtle twist over cosmic distances could cascade across billions of light years to us. It feels invisible, but on a universal scale, it could shape the geometry of everything. To test these theories, NASA and ESA continue to map the universe in increasing detail. The James Webb Space Telescope is already capturing the light of galaxies that formed just 300 million years after the Big Bang. Some of these ancient systems already show organized rotation spiral patterns, far too early in cosmic history to be explained by chance. That means the seeds of spin were planted almost immediately. The universe didn't have to learn to rotate. It was born turning. Even on the quantum level, spin is fundamental. Every particle, electrons, protons, neutrons, carries intrinsic spin, a built-in property of matter described by quantum mechanics. It's not the kind of spinning we can picture, not a ball rotating in space, but a deeper mathematical rotation encoded in the wave function of the particle itself. As physicist Richard Feynman once said, spin is one of the most profound properties of nature. It is not that the particle is literally spinning, it simply has spin as it has mass, as it has charge. It simply is. So in a way, rotation was not added to the universe. Later, it was part of the blueprint written into the first line of existence before anything else was written at all. When you look at the night sky, You're seeing the inheritance of that motion. Every galaxy's swirl, every planet's orbit, every photon of light descends from that first cosmic rotation. Without it, matter would never have clumped, stars would never have formed, and time itself would have no rhythm, no arrow, no direction to follow. So take a breath. Now somewhere deep inside you, the original spin still moves, carrying forward a memory older than the sun, and we carry it without knowing, quietly, everywhere we go. Part 3 does the universe have a heartbeat? Close your eyes for a moment and listen. Your heart is beating somewhere between 60 and 100 times per minute. A rhythm so familiar that you only notice it when something goes wrong. But that rhythm, that steady, quiet pulse, is not yours alone. It echoes something far older, something that began before the first star, before the first atom. The universe has its own heartbeat, written in the language of rotation and resonance, and it has been beating since before time had a name. In physics, a heartbeat is a cycle, a motion that repeats, that returns to its starting point and begins again. By this definition, the universe is full of heartbeats at every possible scale, at the smallest scale inside the atom. Electrons orbit their nuclei in cycles not circular, but shaped like strange, beautiful clouds. Probability waves endlessly vibrating, each oscillation completing millions of billions of cycles every second faster than any clock we can build. Level-up molecules vibrate their bonds, stretching and compressing at frequencies determined by their mass and the strength of their bonds. When light strikes these molecules, it is absorbed at those specific frequencies. This is the principle that allows scientists to read the chemical composition of a distant star or the atmosphere of a world 120 light-years away. The heartbeat of molecules written in light at the planetary scale. The Earth's rotation is a heartbeat, a 24-hour pulse that defines day and night, light and dark, waking and sleeping. Almost every living thing on this planet has organized its biology around that rhythm. Your body knows it in the rise and fall of cortisol, with the morning light in the deepening of melatonin, as the sky darkens in the cycle of your body temperature, which peaks in late afternoon and falls toward its lowest point in the deepest hours of the night. You are synchronized to a planetary heartbeat, one that has been beating for 4.5 billion years. NASA's study of circadian biology, the science of biological clocks, has shown that these rhythms are not just habits. They are encoded in the DNA of nearly every living organism, from the simplest bacteria to the most complex mammals. The Earth's rotation left its signature in the very chemistry of life beyond the day. There is the year Earth's annual orbit around the Sun, a pulse of 365 days that drives the seasons, the migrations, the flowerings and dormancies of life across every continent. Trees ring themselves with it one year, one ring a heartbeat, preserved in wood and beyond the year. At a timescale we can barely imagine, there is the galactic heartbeat, the Milky Way's rotation period of 230 million years. One cosmic year, the last time the sun completed such a journey, the dinosaurs had only just appeared. The Atlantic Ocean didn't exist, and the continents were still pressed together in a single vast land. But the universe's heartbeat is not only in rotation, it lives in the oscillation of stars. Pulsating stars, known as Cepheid variables, breathe in and out with extraordinary regularity, swelling and contracting over periods of days to weeks, changing in brightness as they do. Astronomers discovered in the early 20th century that the period of this pulsation is directly related to the star's true luminosity. How bright it actually is. Not just how bright it appears. This made Cepheid variables cosmic rulers by measuring how long their heartbeat takes. Astronomers can calculate how far away they are. They were the tools that first revealed that the Andromeda galaxy was not a nearby cloud of gas, but a separate galaxy, millions of light years away, a whole other island of stars. A discovery that changed our understanding of the scale of everything. pulsars carry a different kind of heartbeat. City-sized neutron stars spinning hundreds of times per second, their beams of radiation sweeping through space like cosmic lighthouses, each one so regular, so precise, that astronomers initially thought they might be signals from an extraterrestrial civilization. They called them LGM's little green men before discovering the physics behind the pulse. Even today, pulsars are used as natural clocks to test the predictions of general relativity. Their heartbeats steady enough to detect distortions in the fabric of space-time itself. Even the sun pulses not as dramatically as a Cepheid, but it oscillates its surface, vibrating with acoustic waves trapped beneath the photosphere, making the entire star ring like a bell in 5-minute cycles. Helioseismologists study these vibrations the way a doctor uses ultrasound to see inside a body. They reveal the sun's interior structure, its rotation, its composition, without ever sending a probe into the inferno. And on the grandest scale, the universe itself may have oscillations. Some cosmological models propose that the universe has gone through cycles of expansion and contraction. Each cycle, a heartbeat. Each Big Bang, a new pulse, a new universe beginning from the ending of the last. This remains one of the most beautiful and contested ideas in physics, but it asks a question that resonates deeply. What if our universe, this vast, spinning, expanding miracle, is just one beat of something even larger? Take a slow breath. Now feel your own heartbeat, if you can. That steady rhythm you carry everywhere without thinking about it is an echo of the Earth's rotation, which is an echo of the solar system's formation, which is an echo of the galaxy's turn, which is an echo of the universe's first pulse. You are not separate from the cosmic heartbeat. You are one of its most local expressions, small, warm, quietly turning in perfect time. Part 4. Can rotation bend time? Imagine for a moment that you are standing perfectly still. No movement, no breath, the world around you frozen, and yet time is passing. The future is arriving moment by moment, one heartbeat at a time. Now imagine that beside you, someone begins to spin slowly at first, then faster, faster, until they are a blur, and you discover when they stop that their clock reads a different time than yours. This is not a story. This is physics Einstein's theory of special relativity, published in 1905. The same year the light from K2-18b left its homeworld showed that time is not a fixed background, not a river that flows equally for everyone. It is elastic, woven into the same fabric as space, and affected by the same forces. Motion slows time, gravity slows time, and rotation as a form of both does. Both the effect is called time dilation, and it has been measured with extraordinary precision, not in thought experiments, but in real experiments with real clocks in real places. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airplanes eastward and westward. When they returned and compared the traveling clocks with identical clocks that had stayed on the ground, the differences were exactly what Einstein's equations predicted. Tiny, measured in billionths of a second, but real, confirming that time itself had moved differently for the clocks in motion. The effect is not academic. It touches your life every single day. The GPS satellites that guide your navigation orbit Earth at about 8,700 miles per hour, 12,500 miles above the surface. At that altitude, they experience weaker gravity than we do at the surface, and because they are moving at high speed relative to us, their atomic clocks run faster by about 38 microseconds per day. If engineers didn't correct for this effect using Einstein's equations, your navigation would accumulate errors of several miles every few hours. Einstein's relativity is not just beautiful mathematics, it is built into every map, app, every delivery route, every flight path that depends on precise location. Now consider what happens near a spinning black hole. A rotating black hole described mathematically by physicist Roy Kerr in 1963 doesn't just curve space-time the way any massive object does. It drags space-time with it like a spoon stirring thick honey, the very fabric of the cosmos pulled around by the rotation of an object so massive that not even light can escape it. This effect is called frame dragging, and it means that near a rotating black hole, space itself is flowing like a river, carrying everything with it. You cannot remain still near such an object any more than a leaf can remain still in a river. The very geometry of space is moving frame. Dragging was confirmed, not near a black hole, but right here around our own quiet Earth, by NASA's Gravity Probe B experiment launched in 2004. The probe carried 4 perfect spheres, the most perfect spheres ever made by human hands as gyroscopes, and measured how their orientation drifted as Earth dragged the space-time around it. The measurement matched Einstein's prediction to within a fraction of a percent our planet. Just by spinning is subtly warping the time and space around it at the extremes of rotation near a black hole, spinning at close to the speed of light. Time dilation becomes profound, an observer hovering just above the ergosphere. The region where frame dragging becomes irresistible would experience time passing at a dramatically different rate than an observer far away. This is not science fiction. This is the mathematics of general relativity tested and confirmed by every gravitational wave detection that the LIGO and Virgo observatories have made. Every collision of 2 black holes, every merger of neutron stars is a test of Einstein's spinning space-time equations, and every time the equations pass, what does it mean that rotation bends time? It means that time is not separate from the physical world. It is part of the same fabric, the same geometry as space and motion. To change how something moves is to change how time flows. For it to set something spinning is to write a different time into its experience. Your own sense of time right now is tied to Earth's gentle spin, to the sun's pull, to the galaxy's slow turn. You are embedded in a web of rotating things, each one bending time by a tiny amount, each one contributing to the particular and unrepeatable flow of time that you experience as your life. And if rotation can bend time, then here is a question that takes the breath away a little. What happens when time starts to control the spin? That is the mystery waiting in our next chapter. Part 5, if spin controls. Time who controls the spin every second you live is shaped by something spinning, the ticking of your watch, the pulse of an atomic clock. Even the rhythm of your heartbeat all depend in some way on something that is turning inside the atomic clocks that define the second for all of humanity. Electrons whirl around atomic nuclei at fixed energy levels. When they jump between those levels, they release photons at an exact frequency. That frequency, defined by the cesium-133 atom, sets the length of 1 second 9,192,631,770 cycles of radiation. That number, printed by the International Bureau of Weights and Measures, describes how every second of your life is calibrated to a tiny atomic spin, to the quantum heartbeat of a single element. The rotation of electrons inside atoms is not the physical spinning. We imagine not a ball turning in space, but a fundamental property of matter, a quantum spin, a kind of internal angular momentum that every particle carries like a fingerprint. This property determines how electrons behave in magnetic fields, how they bond to other atoms, how they obey the Pauli exclusion principle, the rule that no 2 electrons can occupy exactly the same quantum state. So, at its smallest scale, our ability to measure time at all depends on spin, not the turning of a planet, but the internal angular momentum of atoms themselves. But just as atomic spins govern time in our laboratories, planetary spins govern time on a cosmic level. The Earth's rotation defines the length of a day. Its orbit around the Sun defines the year. These motions aren't fixed. They drift. Tidal forces from the Moon are gradually slowing Earth's spin. adding 1.7 milliseconds per century to each day. To keep atomic time and planetary time synchronized, scientists use a system called leap seconds. Occasionally, the world's atomic clocks are adjusted by 1 second to align with the planet's natural rotation. In a sense, we are constantly recalibrating human time to match Earth's cosmic spin, an act of extraordinary humility, acknowledging that our clocks, as perfect as we have made them, must still bow to the turning of the world. If you compare clocks at different latitudes, the differences are measurable. A clock placed at sea level near the equator, moving fastest due to Earth's spin runs, slightly slower than one placed high in the mountains or near the poles. This is both special and general relativity at work. As NASA explains, a clock on the equator ticks more slowly than one at the poles, because it's moving faster and sitting deeper in Earth's gravitational potential. The difference is tiny, a few nanoseconds per day, but real, and your phone, every time it gives you a location, is quietly correcting for it. Each of the 24 GPS satellites orbits Earth at about 8,700 miles per hour, 12,500 miles above the surface. In orbit, they experience weaker gravity and higher speed, causing their onboard atomic clocks to run faster than clocks on the ground by about 38 microseconds per day. If uncorrected, this would make navigation errors of several miles accumulate every few hours to keep time. Consistent engineers combine Einstein's equations with real-world measurements, literally adjusting for the curvature of space-time caused by Earth's rotation. So every time you find your way somewhere, every time a delivery arrives at a door, every time an aircraft lands, you are witnessing relativity in action, a quiet collaboration between gravity, motion, and spin. But who started the spin in the first place? Astronomers trace it back to angular momentum, a conserved quantity in physics when the solar system formed 4.6 billion years ago. A cloud of gas and dust, vast and quiet, collapsed under gravity as it shrank. It spun faster, just like a skater pulling in her arms, that primordial motion distributed angular momentum to everything inside the sun. The planets, their moons, each body still carries a portion of that ancient rotation. No external force continually keeps them spinning. They continue because of inertia, because in space, where friction is nearly absent, spins can last for billions of years without anyone or anything pushing them. So the answer to who controls spin is quiet and complete. No one once set in motion, the universe needs no hand to keep turning. It carries itself forward by the same laws that set it moving in the first place. The relationship between spin and time grows stranger. The deeper we look inside, atom spin determines energy states, and energy states determine time on planetary scales. Spin defines days on cosmic scales. Spin drags time itself through the phenomenon of frame dragging, and all these levels are connected by one law: angular momentum is conserved. Time, in that sense, is not an independent entity flowing apart from the physical world. It is a reflection of how energy and spin interact, a shadow cast by motion onto the screen of existence. In 2016, ESA's Gaia mission mapped the precise motions of over 1 billion stars in the Milky Way. The data revealed that our entire galaxy rotates once every 230 million years, carrying the Sun and its planets along in a vast spiral, each star's orbit contributing to a grand cosmic timepiece, one rotation marking the rhythm of galactic time. Just as atomic spin defines seconds, stellar spin defines aeons. Even the Sun spins once every 27 days at its equator, but not uniformly. Its poles rotate more slowly, a phenomenon called differential rotation. This twisting motion generates magnetic fields that shape solar flares and coronal mass ejections. When those magnetic storms reach Earth, they distort our magnetic field and can affect satellites and power grids from the atomic scale to the solar scale. Spin is not passive, It sculpts fields, defines rhythms, and interacts with everything we build to measure and navigate the world. Take a breath. Now the atoms within you are spinning in harmony with the turning Earth, the orbiting moon, the spiraling galaxy. You are already part of that motion. Every heartbeat a fraction of a universal rhythm that began long before clocks, calendars, or light itself. Part 6 did the universe. Begin because symmetry was broken. Imagine a universe of perfect balance. A universe where everything was equal, where every force was exactly matched, where matter and antimatter were identical in number, where every push was answered by an equal pull, where nothing had a reason to begin and nothing had a reason to end. In such a universe, there would be no motion, no stars, no atoms, no time, only stillness, endless and unchanging, perfectly balanced, perfectly empty the universe. We know began not with perfection but with a tiny imperfection, a small crack in symmetry, a flaw so slight that a trillion measurements might miss it. But that was enough. That flaw, that one asymmetry in the infinite whole, allowed everything to unfold. In physics, symmetry means that the laws of nature behave the same way in every direction, at every point, and for every observer. When symmetry holds perfectly, nothing has a reason to change. But when it breaks, even slightly, motion appears, structure emerges, and time gains. Direction, as NASA's Goddard Space Flight Center describes. The universe exists as we know it because perfect symmetry didn't last. Let's drift back to the first fractions of a second after the Big Bang. According to the standard model of particle physics, the early universe was a hot, dense plasma, where the four fundamental forces were once unified, a single, seamless whole. But as the universe expanded and cooled, these forces began to separate. This process, called spontaneous symmetry breaking, shaped everything from the structure of atoms to the fabric of space-time itself. ESA's Planck mission mapped the cosmic microwave background, the faint afterglow of the Big Bang, and found it was astonishingly uniform, yet not perfect. Tiny variations in temperature, only 1 part in 100,000, reveal the first signs of broken symmetry. Those minute differences in energy density later grew into galaxies, stars, and planets. Without those fluctuations, the universe would remain smooth and static, an endless, featureless mist, and none of us and none of this would exist. Even matter itself owes its existence to broken symmetry. When the universe was young, it created matter and antimatter in nearly equal amounts. But nearly is the key for every billion particles of antimatter. There were 1,000,000,001 of matter. That slight imbalance, known as baryon asymmetry, meant that when matter and antimatter annihilated each other, a tiny fraction of matter survived that leftover matter. That 1 in a billion survivor became the stars, the planets, and everything we see today. You exist because the universe wasn't perfectly fair, because one side had 1 extra particle in 1,000,000,000 that survived. In 1964, physicists James Cronin and Val Fitch discovered this subtle asymmetry in particle behavior, an effect now called CP violation. Their experiment with neutral kaons showed that the laws of physics treat matter and antimatter slightly differently. This discovery earned them the Nobel Prize and provided the first clue that the universe prefers one direction, one spin, one imbalance, as ESA's Particle Physics Division notes. Without CP violation, the universe would contain no matter, only light, an empty brilliance with nothing to receive it. The mechanism behind this imbalance is still being studied at CERN. The Large Hadron Collider investigates particles like the Higgs boson, which plays a crucial role in breaking electroweak symmetry. When the universe cooled below a critical temperature about 10 to the power of -12 seconds after the Big Bang, the Higgs field gained a non-zero value everywhere in space. That field gives particles mass and breaks the symmetry between light and matter. It's often said that the Higgs field froze the universe into its current form, locking in the differences that made complexity possible. Not all symmetry breaking is violent. Sometimes it's gentle, like the way a perfectly balanced pencil will eventually fall in one direction. Not because anything pushed it, but because perfect balance cannot be maintained forever in a world that breathes. The universe may have chosen a direction for time in a similar way. In the earliest instant, time could have flowed equally forward or backward. But a tiny fluctuation, perhaps in entropy, perhaps in quantum probability, pushed it forward, setting the arrow of time. And that arrow has been flying ever since, through every moment, every life, every star, as physicist Sean Carroll once wrote. The arrow of time is the result of low entropy at the beginning of the universe, a state of broken symmetry that all later moments remember. So when we measure time, we are really measuring how far we've drifted from that original, perfect stillness. Even the cosmic web, the vast structure of filaments connecting galaxies, arises from this imbalance. JWST's deep field images show galaxies forming along invisible threads of dark matter that trace the earliest quantum fluctuations in density. Those fluctuations began as random variations magnified by cosmic inflation just moments after the Big Bang. What began as tiny irregularities became the architecture of the universe, the scaffolding of everything. Without a symmetry, gravity itself could not work the way it does. A perfectly uniform distribution of matter would pull equally in all directions, producing no motion, no collapse, no stars. But with slight unevenness, gravity could act, drawing matter into clusters, forming galaxies, stars, and eventually the quiet worlds where life can breathe. Even at the quantum level, particles betray the same imbalance: neutrinos. Those ghostly particles that pass through everything without stopping are known to have chirality. They all spin in the same left-handed direction. Not some left and some right, all left. This handedness of the universe may be another echo of the original symmetry. Breaking the universe chose a direction, and every neutrino, every one that passes through your body right now, trillions per second, carries that choice into the future. Take a slow breath. The universe you inhabit was made possible by imperfection, by one extra particle in a billion, by a pencil that fell, by an arrow of time that chose to fly forward. And in that imperfection, in that slight imbalance, you exist. Reading these words in the light of a sun that was born from a cloud, that turned in a galaxy, that spins in a universe, that tilted ever so slightly and became everything. Part 7 is every spiral in nature, an echo of the cosmos. Take a slow breath and think about the last spiral. You noticed perhaps it was the curl of a shell on a beach. A perfect logarithmic curve, adding chamber after chamber as its inhabitant grew each new room a little larger, a little further from the center, following a proportion that mathematicians call the golden ratio, written into the shell without measuring, without calculating, simply by growing. Or perhaps it was a fern uncurling in the morning light, its fronds tightly wound, then slowly opening each smaller frond, a miniature of the whole. The same spiral repeated at every scale, or a galaxy seen edge-on in a photograph, a disk of light with luminous arms curving outward into the dark. The same elegant sweep, the same proportion written in stars. Is this a coincidence? Or is it something deeper in mathematics? The logarithmic spiral is the shape that appears when growth and rotation are combined, when something expands outward while turning it naturally. Traces this path without effort, without intention, simply as a consequence of the rules. It follows. A galaxy forms this shape, because as stars in the outer arms take longer to complete an orbit than those in the center, the structure winds slowly over billions of years into the arms. We see a shell forms this shape. Because as the organism grows, it adds material at a constant angle, never changing its proportion, only its size. A fern forms this shape because the most compact way to pack new growth before it unfurls is to roll it inward. Different systems, different scales, the same mathematics, NASA's studies of galactic structure have found that spiral arms in galaxies follow density waves, not fixed structures of stars, but waves of increased density that move through the disk like ripples on water. As stars pass through these waves, they are compressed slightly, triggering new star formation. The bright, hot, young stars illuminate the wave, making the arms visible. The arms are not permanent features, they are patterns the way a wave is a pattern in the ocean, not a fixed collection of water, but a moving shape that the water briefly takes and then releases in living systems. The spiral appears wherever growth meets boundary, wherever a living thing must expand within a limited space while remaining functional. The double helix of DNA, two strands wound around each other, is a spiral. It is the most efficient way to pack an enormous amount of information into an extraordinarily small space. The human genome uncoiled would stretch about 2 meters, yet it fits inside a cell nucleus about 6 micrometers across, packed into a spiral that can be read and copied and expressed without tangling, without breaking, with extraordinary reliability over billions of cellular generations. The inner ear, that small spiral chamber, the cochlea, is wound in the shape that allows the widest range of frequencies to be sorted in the smallest possible space. Low frequencies at the apex, high frequencies at the base. The coiling allows a membrane that would need to be enormous if laid flat to fit within a shell smaller than a fingertip. The eye of a hurricane is a spiral because rotation and inward movement produce the same mathematics as a galaxy as a shell. As a cochlea, warm, moist air flows inward, while the Earth's rotation deflects it sideways, creating the great turning spiral. Visible from space, a pattern that the atmosphere borrows from the same physics that shapes the Milky Way. Sunflowers arrange their seeds in spirals of 2 adjacent Fibonacci numbers, 34 spirals in one direction, 55 in another, or 55 and 89, depending on the size of the flower. This arrangement packs the maximum number of seeds into the available space with no wasted area, no gaps, no overlaps. The mathematics of the universe expressed in a flower in a field in summer. ESA, scientists studying the distribution of galaxies across the cosmic web, have found that the filaments and voids that make up the large-scale structure of the universe show patterns consistent with the same recursive mathematics, the same self-similarity that appears in fractals and in living things. The universe, from the smallest shell to the largest cosmic filament, seems to favor certain shapes, certain proportions, certain ways of growing and expanding and turning. Is this because the same physics, the same rules of angular momentum, conservation of energy, and the mathematics of growth apply at every scale? Yes, but perhaps it is also because the universe had a preferred geometry from the beginning, a direction, a handedness, a way of turning that every system inherits from the original spin of everything. When you see a spiral in a shell, in a fern, in a galaxy, in the water draining from a sink, you are seeing the universe remembering how it began, the same shape appearing again and again, because the laws that produced the first spiral are the same laws that produce every spiral after. You are seeing the cosmos in miniature in a shell in your hand. Part 8. Did the universe's spin decide the direction of life? There is a question in biology so simple, it seems almost naive, and yet so profound that it has occupied scientists for more than a century. Why does life go in one direction? Not philosophically, not metaphorically, but literally. Physically, chemically, why does life turn left, the molecules that make life possible? The amino acids that build every protein in every organism on this planet are almost exclusively left-handed in chemistry. This property is called chirality. From the Greek word for hand, a chiral molecule is one that comes in 2 mirror image versions, like a left hand and a right hand, structurally identical, but not superimposable, not interchangeable, like a glove that fits one hand and not the other in the laboratory. When chemists synthesize amino acids without any biological template, they get an equal mixture, half left-handed, half right-handed, no preference, no direction, pure symmetry. But in life, the story is different. All 20 standard amino acids used by living organisms are left-handed without exception across every domain of life. Bacteria, archaeoplants, animals, the preference is absolute. If you could somehow build a protein from right-handed amino acids and introduce it into a cell, the cell would not know what to do with it. Its enzymes would not recognize it. Its ribosomes would not read it. It would be as incomprehensible as a text written in the mirror. Why one of the most compelling answers reaches up from biology, through chemistry, through physics, all the way to the cosmos, to the handedness of the universe itself, neutrinos. Those ghostly subatomic particles that pass through matter. As if it weren't, there are all left-handed, every single one. This is not an approximation. It is a fundamental property of how the universe works. The weak nuclear force which governs certain radioactive decays treats left-handed and right-handed particles differently. It has a preference built into the laws of physics, a cosmic handedness. This preference for left written into the deep structure of matter produces a tiny but real difference in how the weak force interacts with left-handed and right-handed molecules. Some researchers believe that over billions of years in the environments where life first formed, this tiny preference driven by the weak nuclear force could have tilted the balance ever so slightly toward left-handed molecules, and that life finding itself in a universe that preferred left simply followed the universe's lead. There is also a role for starlight light from stars, and particularly from certain types of young stellar environments, can be circularly polarized, spinning in one direction as it travels through space, and circularly polarized light interacts differently with left-handed and right-handed molecules. It destroys one type slightly faster than the other. NASA's study of interstellar organic chemistry has found that in certain regions of space, the polarization of starlight could create an excess of one amino acid chirality over billions of years. Those chiral molecules delivered to early Earth by meteorites and comets could have seeded the planet with a slight excess of left-handed forms, and life beginning in that environment built itself from the molecules it found inheriting the handedness of the cosmos. This theory receives support from meteorite analysis. In the Murchison meteorite, which fell in Australia in 1969, scientists found amino acids formed in space before Earth was even born, and those amino acids showed a slight excess of the left-handed form. Not large, not overwhelming, just a slight tilt, but consistent with the idea that the universe, through the handedness of its light and the chirality of its particles, gently predisposed the chemistry of life toward the left. SA observations of star-forming regions have found that the polarized light surrounding young stars can produce exactly this effect on complex organic molecules. The seeds of life drifting through interstellar space may have been chirally sorted by the spin of starlight before they ever reached a planet, before life began. The universe was already tilting the table, choosing a direction, and every living thing since has been following that choice. So when we ask whether the universe's spin decided the direction of life, the evidence points to a quiet yes, from the spin of galaxies to the handedness of neutrinos, from polarized light to chiral molecules in meteorites. Every scale of nature seems to prefer motion in one direction. It's as if life is not random at all, but a continuation of the universe's earliest rotation, written into every strand of DNA, into every protein, into every heartbeat of every living thing that has ever breathed. As Carl Sagan once said, "We are made of star stuff. Perhaps we are also made of the spin of those stars, the angular memory of their light written into us before we had any way to read it." Take a quiet breath. Every cell inside you still carries that twist, a microscopic echo of the universe's turning. From the dance of galaxies to the spiral of your DNA, the same motion continues, smooth and silent across billions of years. Part 9. Will the universe forget how to spin? Everything slows. The Earth's days are growing longer by 1.7 milliseconds every century. A change so small it would take hundreds of millions of years to feel, but real and accumulating without pause. Galaxies are drifting apart, their graceful spirals losing cohesion as dark energy. The mysterious force accelerating the expansion of the universe stretches the spaces between them wider and wider into an expanding emptiness. The stars themselves, those furnaces of motion and fusion, are burning down one by one, converting hydrogen to helium, helium to heavier elements, and eventually running out of fuel to die in silence or in extraordinary violence depending on their mass. The universe that began with a great spin seems slowly to be unwinding, but can motion truly vanish? Or does it simply fade, spreading thinner and thinner across the fabric of space until it becomes imperceptible but never truly gone? NASA physicist Michel Thaler once said, "Energy doesn't disappear. It disperses so too with spin. It doesn't stop, it diffuses. Our planet is already losing its rhythm each century. The Moon's gravitational pull slows Earth's rotation by about 1.7 milliseconds, transferring that energy outward. The result is that the Moon drifts away from us by nearly 1.5 inches every year, a gentle separation confirmed by laser reflectors left on the lunar surface by Apollo astronauts whose beams we bounce light off and measure the return time. With millimeter precision, if this process continues, Earth's rotation will one day lock with the Moon's orbit, each always showing the same face to the other as the Moon already does to us. It will be the end of tides as we know them, the end of the daily cycle of ocean and air and light. Planetary spin, once vibrant, will fade into equilibrium, a long, slow stillness that is not death, but something like sleep. Elsewhere in the solar system, the same story plays out. Mercury is already trapped in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the Sun. Venus, with its dense atmosphere, has slowed to an almost unearthly crawl. 1 rotation every 243 Earth days, and in the opposite direction of its orbit. Even Mars, whose day is only slightly longer than ours, is gradually losing speed over cosmic time. Scale spin is not forever. It is a rhythm winding down. The slowing continues beyond planets into the heart of galaxies using the Hubble Space Telescope and the Very Large Telescope in Chile. Astronomers have measured the rotation of spiral galaxies billions of light years away. When compared with modern galaxies, those ancient systems appear to have spun faster, tighter arms, denser cores, more angular momentum. As time passes, gravitational interactions and cosmic expansion gradually sap that motion, the spiral giving way slowly to the ellipse, according to a 2020 study from the Leibniz Institute for Astrophysics. Potsdam galaxies may lose a significant portion of their spin through collisions and mergers. When 2 galaxies merge, their stars don't crash into each other, but their dark matter halos interact, redistributing angular momentum outward. This process leaves galaxies rounder, slower, and more diffuse, the graceful spiral becoming a featureless oval, vast and quiet. The European Space Agency's Gaia mission has mapped over 1.8 billion stars in the Milky Way, revealing that even our galaxy is evolving towards stillness. Its outer arms, once tightly wound, are gradually stretching over billions of years. Friction with dark matter and nearby galaxies will drain its spin, softening its spiral form. Eventually, the Milky Way and Andromeda will collide, not in chaos, but in slow, silent fusion, their combined rotation settling into a single, massive, nearly motionless elliptical galaxy that no longer turns fast enough to form new stars. But spin doesn't vanish when the stars fade. It transforms when a massive star dies. It collapses inward, conserving angular momentum, spinning faster than ever before. This creates neutron stars, city-sized objects that can rotate hundreds of times per second. NASA's NICER instrument on the International Space Station has observed pulsars spinning 716 times per second, their beams sweeping through space with the precision of atomic clocks. Yet even these cosmic lighthouses eventually slow, radiating away energy as gravitational waves and magnetic fields, their tremendous spin given to the universe, one pulse at a time as time expands further. Rotation becomes scarce, stars fade. Black holes, the last great engines of spin, slowly evaporate through Hawking radiation in 1974. Stephen Hawking predicted that even black holes are not eternal. They leak energy and lose angular momentum over unimaginable time. Scales a spinning black hole known as a Kerr black hole, gradually transfers its rotation to surrounding space, leaving faint ripples of energy that stretch across the universe. ESA's LISA mission planned for the 2030s will detect these gravitational whispers waves caused by spinning black holes merging and fading. Each detection a record of rotation being released into a space-time, echoing across billions of light years. Even when the black holes themselves are gone, their rotational memory will remain imprinted in the geometry of the universe, like fossils, like fingerprints in stone. So will the universe ever truly stop spinning. Not completely angular momentum cannot be destroyed, only spread thinner, shared among an ever-expanding sea of particles. As NASA explains, in an isolated system, angular momentum is conserved. The universe, in this sense, never stops moving. It only redistributes motion, scattering it, thinning it, spreading it across an ever larger canvas, until each piece becomes too faint to measure, but never truly zero. Still, there may come an age when motion becomes imperceptible in the far future, long after the last stars have died and galaxies have faded. The universe will enter what physicists call heat death. Energy will be evenly distributed. There will be no temperature gradients, no flow, no reason for anything to move. Rotation will persist mathematically. But without contrast or structure, it will have no meaning. Motion without a witness, spin without a sky. Some cosmologists describe this as the cosmic silence, the final calm after every vibration, every orbit, every spin in that distant epoch. Protons themselves may decay, and black holes may fade into bursts of radiation. Only faint background photons and neutrinos will drift endlessly through space, carrying the last traces of the universe's once grand rotation. Take a long, slow breath right now. The Earth's core still turns, the stars still orbit, and the Milky Way still drifts through the darkness. Every motion you know is a flicker of that ancient rotation, one that will outlast you, but not eternity. And when that eternity arrives, when the last spin finally stretches into silence, something else will still remain, not movement but the memory of movement. Because even when the universe forgets how to turn its geometry, we'll still remember that it once did. Part 10, Are We the Universe Remembering Its Own Motion? Every atom inside you is spinning. The electrons orbiting your nuclei, the protons and neutrons inside them, the quarks deep within, all are caught in ceaseless motion. That motion isn't random, it's a continuation, the faint echo of the universe's first rotation, the original turn carried forward through every generation of matter to here to you to this moment when you move, when you breathe, when your heart beats. You are not separate from the cosmos. You're part of its oldest memory motion, itself preserved in chemistry, in biology, in consciousness, in the simple fact that you are here and aware of being here in physics. Angular momentum is the persistence of spin, the rule that keeps motion alive. It's why galaxies still turn, why planets still orbit, and why atoms still vibrate. After 13.8 billion years, according to NASA's Goddard Space Flight Center, angular momentum cannot be destroyed, only transferred or shared. That means every spin in the universe, from the grandest galaxy to the smallest particle, is a continuation of the same original rotation that began at the Big Bang. The same motion, different scales, different forms, but one unbroken chain, reaching from the first moment to this one. In the beginning, the universe was not still. Measurements from ESA's Planck satellite show that the cosmic microwave background, the faint afterglow of the Big Bang, carries subtle anisotropies, slight directional differences in temperature. Some cosmologists interpret these as traces of the universe's first angular momentum, the original twist that set everything in motion. That primordial spin never vanished. It fragmented, spreading across scales from galaxies to atoms, from stars to cells, from the turning of a solar system to the turning of a thought. When stars form clouds of hydrogen and helium, collapse under gravity as they shrink, they rotate faster, conserving angular momentum like an ice skater pulling in her arms. This same rule gives rise to accretion disks around young stars, to planetary systems, to the rings of Saturn, to the delicate geometry of a snowflake. Each planet, each moon, carries a fragment of that spin embedded in its orbit, and within those planets, inside every rock, every ocean, every living cell, the pattern continues at smaller and smaller scales, but always the same pattern, always the same motion. Our atoms, too, hold rotational memory. The electrons that define chemical bonds obey the quantum property of spin, a fundamental angular momentum intrinsic to all particles. This spin isn't literal spinning, but a quantum state, a value that determines how particles interact with magnetic fields. Without it, chemistry would not exist. NASA's Quantum Laboratory Initiative describes spin as the engine of atomic structure, the difference between chaos and stability. In this sense, you could say every piece of matter carries an ancient choreography. The spin of particles leads to magnetic fields, which lead to structure, which leads to stars and planets, and ultimately to life. Your neurons fire using electrical potentials shaped by these same fields. Every thought that crosses your mind is an alignment of charged particles, a kind of ordered motion, a tiny spin in the long chain of spins that began at the beginning of everything. So when we ask whether consciousness might be the universe, remembering its motion, the question isn't only poetic, it's physical. Each brainwave, each signal, each moment of awareness is built upon rotations that have existed since the dawn of time. The magnetic fields generated by your neurons are faint echoes of the same electromagnetic principles that guide pulsars and magnetars and the great rotating engines of the cosmos. As astrophysicist Neil deGrasse Tyson said, "We are not in the universe. We are part of the universe, and the universe is in us." From a scientific view, memory is a form of pattern preservation information encoded in physical states. Atoms remember through spin orientation, cells remember through molecular structure, stars remember through rotation curves, and the universe remembers through the geometry of space-time itself. Einstein's general relativity teaches that energy and momentum shape the curvature of space-time. Every movement, every rotation leaves a small indentation, a swirl in the geometry of reality. This is known as frame dragging, confirmed by NASA's Gravity Probe B experiment in 2011. The probe measured how Earth's rotation subtly twists the surrounding space-time like a spoon stirring honey. It proved that spin isn't confined to objects. It extends into the very fabric of the cosmos, into the space around things, into the shape of everything in a similar way. Even your movements, though infinitesimal, also disturb space-time ever so slightly. The difference is just scale. Your body's atoms spin billions of times per second, generating magnetic interactions measurable by quantum sensors, each micro-rotation contributing to the ongoing record of motion that began long before humanity existed. If all motion leaves traces in space-time, then perhaps what we call awareness is the way the universe perceives those traces through us, not as emotion or spirit, but as physical continuity matter, recognizing its own persistence. Consciousness in this purely scientific sense is the system's capacity to reflect its internal state, and that reflection is written in movement, even light. The messenger of the cosmos carries angular momentum, photons possess spin, which determines how they polarize and interact with matter polarization patterns across the cosmic microwave background act as the oldest record of rotational memory in existence. ESA's Planck satellite and NASA's WMAP mission mapped these swirls in exquisite detail, showing faint B-mode patterns, signatures of primordial gravitational waves rippling from the universe's first motion. So when you gaze at starlight, you're literally seeing the memory of spin light, twisted and stretched by billions of years of motion. And that light enters your eyes, triggers chemical reactions and becomes part of your own neural motion. In that way, the universe doesn't just remember its spin, it continues to experience it through every observer. It creates through every pair of eyes that looks up. Even as the cosmos expands and cools, these traces persist. Galaxies may slow, but their angular momentum never disappears. It's passed to intergalactic gas, to dark matter halos, to radiation, to light. To us, the JWST has detected faint filaments of gas stretching between ancient galaxies, structures shaped by those very transfers of spin. Every wisp of matter still moves to the rhythm set 13.8 billion years ago. And when the last stars fade and motion becomes silence, those patterns encoded in gravitational waves in particle spin in frozen light will still ripple faintly through empty space. They are not gone, they are written into the shape of everything that remains. Like fossils of rotation, they form the universe's deepest kind of memory motion preserved as geometry. Carl Sagan once reflected, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself in the language of physics, that knowing is not mystical. It's informational through motion energy and spin. The universe continuously encodes and retrieves its own history. Take a breath slowly. Every atom inside you continues to turn the same spin that once ignited the first stars. You are a moving archive, a living part of the universe's ongoing memory. And as we follow that idea, that motion may be the cosmos. Remembering itself, a new horizon opens, because if memory is movement, then perhaps what we call life is the brief moment when the universe pauses just long enough to notice it's still spinning. And perhaps that is enough to call it beautiful if this quiet journey has brought you even a small moment of peace. I'm deeply grateful you've spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It's what keeps me creating these cosmic lullabies for wandering minds like yours. And if you're kind enough, please tell me in the comments where you are tonight and what time it is, where you're listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they're like little stars guiding me forward, and I treasure them deeply until next time. May the universe turn softly around you.